So this is a video explanation of number 1 from the Newton's second law practice problem worksheet. In this problem we have a 75 kilogram astronaut sitting in a rocket ship. There's our astronaut. And we know that this astronaut is going to be accelerated upward during blast off. So there's this blast off. And we are told the following information. We're given the mass of the astronaut, and that is a 75 kilogram person. And we're given some indirect information that's going to lead us to acceleration. We're told that the rocket starts at rest, so that's V initial. And we know that after a certain time interval of 14 seconds, the astronaut reaches a final speed or top speed of 162 meters per second. What this information here is going to tell us is the acceleration upward. Let me write that meter for you. The acceleration upward of the astronaut during blastoff. So let's go ahead and do that calculation. So this is question A. Calculate acceleration during blast off. So I'm going to go back a couple weeks and use the relationship that A is the change in velocity over the change in time. Our change in velocity is starting at 0, ending at 162. And that happened in 14 seconds. So if I complete that calculation, see that the astronaut has a positive 11.57 meters per second of acceleration. So this is upwards. Now, next thing we need to do is draw a force diagram. So there's our astronaut represented by the dot. We know we have weight going down. And there's going to be a support force pushing the astronaut up. And I need to make that force longer, in fact much longer than the weight going down, because the astronaut has an overall net upward force. The fact that the upward acceleration is positive 11.57 meters per second squared means that there is an upward net force. So support force has to be greater than weight. Positive net force. Now, the next part of the question asks us to calculate the astronaut's weight. This is pretty straightforward. We know that weight is the specialized case of second law. Weight equals mg. We were told the mass was 75 kilograms. G is 10 meters per second squared. The astronaut's weight is 750 newtons, but I want to be careful here. I'm going to put a negative sign in to remind myself that weight, maybe that's better, weight goes downward. We've shown that in the diagram, but it's helpful to note it in the numbers too. Now, here comes the hard part, or this is I think the trickier part of the problem. Calculating the apparent weight or the support force of the astronaut. So what you're being asked for here is, how hard does the astronaut's seat push on him or her during takeoff? So calculate apparent weight. Or support force. This is very similar to what you did in the elevator on Parents' Day, where the mass was pushed upward by the scale, and the scale provided a support force reading. So I'm actually going to go back to my force diagram, and from the force diagram, I'm going to write a net force statement. So from the force diagram, I can see that net force equals support force minus weight. Notice I'm including the negative sign right now. I'm writing minus W. So when I'm going to try to solve for support force in this problem. So this is my unknown that I'm trying to solve for. I know W is 750 newtons. We've already put the negative sign in, so I don't need to add it in again. In the left-hand side of the equation, the expression is net force. We know what net force is from Newton's second law. It's m times a. So I'm using second law here. The mass is 75 kilograms. That was given. And remember that in part A, we calculated the acceleration. And that was 11.57 meters per second squared. At this point, I can solve for my unknown. So this side of the equation is 867.75. When we multiply kilograms times 11.57 meters per second squared, right, and I do that math out, I get newtons as the unit. And I can solve for support force here. And I get 1,617.75. That's my final answer. Now, some interesting things to note. The support force is 867 newtons greater than the weight. Those extra (867 newtons) are responsible for creating the acceleration of 11.57 meters per second squared. And this is the end of this problem.